Hello and welcome to Physics with Amol sir. So this video is for class 12th and we will continue with our chapter of electrostatic potential and capacitance. Today we are going to talk about the potential energy of a dipole in an electric field and the concept of polarization. So let's begin. Okay, so consider this is a uniform electric field. In this uniform electric field we have placed our dipole. So this is minus q and here we have plus q. This is our dipole which has the length twice a. This dipole is making an angle theta with the electric field. So when we say dipole is making angle means we are talking about the angle of the dipole moment vector with the electric field. Okay, so P is making angle of theta with the electric field. Fine. So we want to find out what is the potential energy of this dipole. Now why would there be potential energy is because this electric field is going to exert a torque on our dipole. Already in the previous class we have seen the torque exerted on our dipole is given by P cross E. Okay, so torque is equal to vector P cross vector E. This is the torque acting on our dipole. So let us say initially the dipole was having some angle. It was here, suppose it was making an angle theta 1. Then after torque was applied, then finally the angle became theta 2. Okay, because of the torque that is exerted. So during this particular change, we want to find out how much will be the work done. Okay, so let's start. To find out work done, we will use the formula W is equal to integral of torque which is a function of theta. Okay, d theta. And what are the limits? Limits we take from theta 1 to some theta 2. Initially we will say it had an angle theta 1. After the torque, because of the torque, it had an angle theta 2. Therefore, the work will be integral of torque is equal to P cross E. Okay, and in terms of its value, we will write it as Pe sin theta d theta between theta 1 to theta 2. Okay, if we solve this integral, you know that integral of sin theta is minus cos theta. Correct? And then therefore this value will become W is equal to P into E into bracket cos of theta 1 minus cos of theta 2. Okay, I think you can understand why we are getting as theta 1 minus cos of theta 2 because of the integral of sin theta is minus cos theta. Okay, and then we can put some arbitrary values for these theta 1 and theta 2. For example, we can take theta 1 as pi by 2. Why we take pi by 2? Because of cos of pi by 2 is 0. Correct? Cos of 90 is 0. So if we assume that our dipole was earlier making an angle of 90 degree with the electric field. Okay, if it was perpendicular to the electric field, what we get is we will get work done is equal to Pe cos of pi by 2 minus cos of theta, whatever is this final theta that we have got now. Cos of pi by 2 is 0. Thereby you will get work is equal to minus Pe cos theta. And if you see P cos theta in the vector form will be nothing but minus P dot E. Okay, so you can say that the work done on the dipole, okay, or the potential energy of the dipole will be given by the dot product of dipole moment and electric field. Okay, so this formula you should remember. So once again, the potential energy of the dipole, okay, we can denote it by U. So U theta, because it is a function of theta, can be written as minus P dot E. This is the formula. Okay, dot product of dipole moment vector and electric field. This formula is important. You can be asked numericals based on this particular formula. For all these concepts, you will find that the answers are already given in our notes, the written notes that I have already provided. Just now when you are looking at the notes, make sure that you are checking the latest CBSE curriculum also that I have already shared. Okay, some of the topics have been deleted. Now, next topic we are going to see is electrostatics of a conductor. So in this concept, we talk about the properties related to electrostatics for conductors. Okay, let us see the concepts one by one. The first property says that electric field inside a conductor is zero. Okay, in the static condition. For example, if you see a conductor like this, okay, this is a charged conductor, right? So let us say we have given some kind of charge to this conductor. It can be positive or it can be negative. Let us say we have given the positive charge. This entire conductor is going to get this positive charge. There will be electric field outside the conductor, definitely. But inside the conductor, okay, the electrostatic field is going to be zero. You will not have any field inside the conductor. Okay, why is that? Electric field, it will move from positive to negative. Inside all these atoms are neutral. Whatever charge is there is only there on the surface. Therefore, inside electric field is going to be zero. Remember. Second property. At the surface of the charged conductor, the electric field must be normal at every point. Means, at all these points, okay, the electric field is going to be perpendicular. Means, if you find this point, okay, and you want to have the direction of electric field, how it will be? It should be perpendicular, 90 degree like this. At this point, let us say at the edge, how will the electric field be? It will be perpendicular again like this. Okay, so at every point on the surface of a charged conductor, the electric field should be normal at that point. This is the second property. Third property, there is no excess charge inside the conductor. This already we have discussed in the first concept also. Okay, whatever charge is there on a charged conductor always lies at the surface, and there is no charge, no excess charge inside. So inside all the atoms or molecules are going to be electrically neutral. Fourth property, the electrostatic potential inside the conductor will have the same value as that on the surface. Means, on the surface if we have a potential of 5 volts, for example, okay, if you go inside, at this point also the potential is going to be 5 volt. In fact, on any point inside, the potential is going to be 5 volt only. Okay, so inside the charged conductor, potential is the same as that on the surface. Property number 5. Electric field on the surface is given by E is equal to sigma by epsilon naught n cap. N cap is a unit vector normal to the surface. Okay, so for any kind of conductor, the electric field on the surface will be given by sigma by epsilon naught. Sigma is the surface charge density. Next property is called as electrostatic shielding. This is important. This property says that if there is a cavity means any kind of hole, okay, inside our charged conductor, then here the electric field is exactly zero. There is no electric field inside the cavity. Electric flux is also zero. There is no flux inside the cavity. But the electrostatic potential V, okay, here if we are having some potential V0, here also the potential will be V0. Okay, it will have potential same as that of the surface, but the electric field inside the cavity is zero. This is called as electrostatic shielding. Now we will talk about concept of dielectrics and polarization. So as I have already told you, dielectrics mean insulators or poor conductors of electricity. Okay, that is the meaning of dielectrics. Why we study dielectrics is because when we place dielectrics in external electric fields, they show some very interesting properties. So imagine this is an external electric field. Okay, external field let us denote by EO. Okay, O let us call it as outside. Okay, the field that is outside, that is external. Here we are going to place a conductor. Okay, so this is a very good conductor of electricity. What will happen because of this electric field? Okay, there will be some charges that will be induced over here. Okay, because electric field is going like this. So on this surface you will see many negative charges. Okay, and on this side you will see many positive charges. So inside you will get an electric field, and electric field direction is always from positive to negative. So there will be an internal electric field going like this, correct? From positive to negative. Let us call this internal electric field by EI. Okay, so you have our external electric field EO and internal electric field EI. Because this is a conductor, okay, this internal field will be exactly equal to the external field. Why? Because it is a good conductor, and because it is a good conductor and internal is equal to external electric field, the total electric field is going to be 0. Making sense? Because you can see the directions are exactly opposite. So total, the overall electric field E will be equal to EO plus EI. Okay, but EI is minus of EO, thereby this will be equal to 0. So resultant electric field for a conductor is going to be 0 inside. Okay, this we are talking about when we have placed it in a external electric field. Now we are going to remove this good conductor, right? So now instead of a good conductor, we are going to place a poor conductor, that is dielectric material. So now we will place a dielectric material over here. Fine. Now dielectric material, it does not have any free electrons, okay, but there will be some amount of charge distribution because of this external field. But what will happen now is the internal field that we have got, okay, whatever field that we get now, this EI will be less than EO. Okay, the internal field, whatever is developed, that will be less than the external field. So the total electric field E will be equal to outside field minus the inside field. So it is not going to be 0. There will be some residual electric field inside. When this happens, we say dielectric has become polarized. Okay, right? So this is the concept of dielectrics. Okay, and reason we study dielectrics is because they get polarized in this manner. Earlier they will not have any electric field sometimes, but after placing an external field, they tend to have a electric field. Now dielectric molecules, they can be of two types, polar or non-polar. If the center of positive and negative charge it is coinciding, that molecule becomes non-polar. For example, let us say hydrogen molecule or oxygen molecule. So in a hydrogen or oxygen molecule, now both these atoms are made up of oxygen. This is an O2 molecule. The center of positive and negative, they are coinciding, they are at the same point. So nowhere is there a distribution of charges. So this becomes a non-polar molecule. Right? There is no polarity, there is no dipole moment. But a molecule like HCl, hydrogen chloride. Okay, in an HCl molecule, you are going to see the positive and negative, they are not coinciding. Okay, the centers of the positive charge and center of negative charge, they are not coinciding. There will be more positive charge towards the hydrogen and less towards the chlorine. So you will see a polarization like this. Basically, this is what is an electric dipole. Right? You can never have one positive charge and one negative charge. ऐसा नहीं होता है. You cannot create dipoles like this. But dipoles exist in this manner. Okay, an HCl molecule is our electric dipole that we have so far talked about. Right? So here it will have a dipole moment from the negative towards the positive. Such molecules, they will be called as the polar molecules. Understanding? So if they are coinciding, non-polar, like hydrogen, oxygen, etc. If they are not coinciding, they are polar. Polar molecules will have dipole moment associated with them. So this box is representing our non-polar molecules. Okay, you can see positive, negative, they are all coinciding. Thereby, total will be 0. There is no polarity. But if we apply an external electric field to our polar molecules, so if external field is applied, in that case these molecules become like this. Okay, what is happening now? The charges are distributing. Okay, you get plus on one side and minus on the other side. So what we have done, we have separated the centers of the positive and negative charge. We have done something called as polarization. Okay, so when polar molecules are placed in external electric field, they show polarity like this. They become polarized, and this is when they are not in an electric field. So this concept of polarizing the molecules, that is creating the positive electric dipoles, that is called as polarization. Okay, and we have a formula to measure polarization. Okay, polarization we defined as the net dipole moment per unit volume of substance. Okay, so what is polarization? We denote it by the symbol capital P. It is a vector. So capital P is equal to net dipole moment. So small p, and I will put the word net. Net means total. Okay, so for a given sample, what is the total dipole moment that you have got? P net divided by capital V, that is volume. Okay, so this is called as the concept of polarization. Fine, you can find the SI unit also. What is the SI unit for dipole moment? Okay, SI unit for dipole moment is Coulomb meter square. Coulomb meter is formula SI unit for dipole moment divided by V. The SI unit is meter cube. So C meter upon meter cube, the unit will be Coulomb per meter square. Okay, so SI unit of polarization is Coulomb per meter square. This also you will remember. We are going to see some simple molecules in this chapter. We are not going to go for complicated cases. Okay, so we are going to see molecules where the polarization is directly proportional to the external electric field. Okay, these are called as linear isotropic dielectrics. Okay, such molecules where P proportional to E, they are called as linear isotropic dielectrics. So as P is proportional to E, we can write P is equal to, this symbol is called as chi. Okay, and this is called as the electric susceptibility. Okay, a big word, but I hope you will understand. Okay, so this electric susceptibility, this is a constant. Okay, it will give us the relation between polarization and electric field. So I hope these concepts have not been too heavy on you. Okay, make sure to go through these concepts in your textbook and in the notes as well. If there are any doubts, please don't forget to ask. Thank you.